going on that lecture, so yes. Now is the screen visible and the voice audible?
Yes, sir.
Yes, sir.
Thank you, guys. So, so this is the question which I gave you. Now let me just remind you what was the question. The question was this, that if I make a coin toss single time and I predict the probability of head getting head from that single toss as compared to if I use the 10 tosses or if I use 100 tosses, how would that be different? And why do we say that if we are doing more and more tosses, then the result is more and more accurate? So what I gave as the homework, that do the coin toss for one time, find the expectation value and the standard deviation related with probability of head. Then do the coin toss for 10 tosses. Again, do the expectation value and the standard deviation and then predict the probability of head. And do the same thing for 100 tosses. So this is the question which we want to attempt. If somebody is not clear with the question, they can just raise this point here. But those who might have done it, did somebody try first question? Did somebody try? No, okay. CLT is part of the internal assessment, by the way. So let's just look into this question. We have coin toss, which is governed by binomial distribution. There are two parameters in the binomial distribution. And we say that let's just toss a coin once. It's a fair coin. So P is half. If I ask you to find out the expectation value of the random variable for n is equal to 1, what will be this? This is something which we did in the class also. How do we do that? Expectation value of a random variable, which is binomially distributed.
Sir, this is x time probability of getting that x.
Okay, so one way is that what you are saying, expectation value is nothing but this. Since it's a PMF which is given, so it's a summation. Yeah, and what will be variance? This mu is nothing but, right?
Yes, sir.
Yes.
One
Yes,
is
sir.
this, but then for the binomial distribution, we already found out the general formula for finding out the expectation value. Do you remember that?
N times
N
P.
N
P,
into
sir.
P.
N times P, and what was the variance?
NP into 1 minus P.
NP into 1 minus P, or standard deviation of the random variable will be NP 1 minus P. So you can directly use this formula because ultimately we found that these are the general formula. Yeah, and the formula were valid for n greater than equal to 1. So let's just come back. Case 1, n. So this I should write now capital N, since this is what I am writing here. So let's say capital N is equal to 1 and P is equal to half. What is expectation value of the random variable?
So 1/2.
Half.
Half. And what is standard deviation? Sigma, let me write. NP 1 minus P
1
over
by
half.
4.
1 into
By
half
2.
to half.
Half.
So that will also be half. I mean, you can just do that. So what is the probability of head? If you have to show that, you will say, sir, since I have done one toss of a coin, so I can just report this half plus minus half as my result, which is nothing but mu plus minus sigma. In fact, you can also find out the fractional error in that. What will be the fractional error? It is nothing but this, and percentage error. That is nothing but 100 times this. So what is fractional error?
1.
1
1.
or 100% error. So now look into what you have said. Let's just think about it. If you just do a coin toss once, you will get either tail or head actually, right? I mean, you will not get this half value from somewhere. You will get one result, either 0 or 1. And what is the error in that? The error in that is almost 100%. So if you are writing 0, then the result will be 0 plus minus 1. If you are writing 1, then also the result will be 1 plus minus 1. So that is the precision with which you find out the probability. If you really do a coin toss, the result which you will have to quote, either the probability of head, experimental one, will be 0 plus minus 1 or 1 plus minus 1, because there is the 100% error in this. Let's see what happens if I do the same coin toss for n is equal to 10. That means I am doing now coin tosses for 10 such, so single coin which is fair, and I'm doing 10 such tosses. Yeah. So when I am doing expectation value of a random variable, what is the value?
5, sir.
5. What will be error in that, or standard deviation?
1.58.
So this will be,
1.58.
yeah, I mean, basically what you are saying should be root 5 divided by 2, right? Yes,
Yes,
no?
sir.
Yeah. So what you are saying that on an average, if you are going to do 10 tosses, then the current result, best result which I can think of is 5 plus minus root 5 over 2. And if I ask you to convert that into probability of head, how will you convert it? How will you convert it?
So divide that number by 10.
Expectation value divided by n.
Yeah. So that is one way of looking into it, which is absolutely justified. What you are saying is, if I want to find out probability of head, this is expectation value divided by n, or you can even think about very simply. In fact, even if you do not remember the formula, then also it is rather simple that when I am considering 10 tosses, each of the toss can be represented by one random variable. So that means x1 to x10 over n. This is what you are actually looking into. Look into it carefully what we have done. That 10 tosses, we already got the result for one toss. So I said that when we are going to do 10 tosses, then I can make a random variable which is x, which is nothing but the average over these 10. And I can use the result from this to build this. It's basically saying the same thing again. If you want to do it, ex1 plus ex2 plus ex10 over 10. And what is the expectation value of each of these individual x1, x2, x3, x10? This is what you have found in the first one.
Half.
1 by 2.
Yeah, so 1 by 2, 1 by 2, which means I am doing it 10 times, divide by 10, or 10 into half divide by 10, which is exactly the number which you have given me, 5 over 10. What is the standard deviation in this number? This random variable which we have built. Okay, now am I still audible?
Yes, sir.
Yes, sir. Yeah, I just try to change my network to get better. Anyway, what will be standard deviation in this variable? How do you get it? I mean, one thing is rather simple, that you knew how to get the probability of head from your expectation value. What did you do? Ex equal to 5 and then you just divide it by n. What will you do for the standard deviation or the variance? So this number you have already got half. How to get it? Of course, you can do this thing, x10 over 10. This is what the, if I want to find out sigma square, this is what the variance would be, right? Each of the coin toss is independent of each other. So can you just guess what the value should come? This formula should be reduced to what? If each of them is independent of each other, each trial is independent.
Sigma square divided by
Right. So sigma square x1 plus sigma square x2 plus up to sigma square x10 divide by what?
100, sir.
That divide by 100. Very good. So 1 by a n. So that will be 1 by n square. And what happens to the covariance terms? x1, x2, x1, x3 up to x1, x10 and then x2. They will
because
all
they
be 0 because they are independent. Now you already know each of the sigma square x1. Yeah, I mean on the previous page you already found out that was sigma square for each one of them was 1 over 4. Sigma was 1 by 4. So this is for each of it. So can you now do that? So what this value will be? 1 by 4 plus 1 by 4. How many times? 10 times. Divide by 100. So 10 into 1 over 4. What is the result?
1 over
1 by
40.
40.
Yeah, 1 over 40, or I write the same thing as 1/10 of 1 by 4. And what will be sigma? 1 over 2. I mean, you write down 1 over 40, there is nothing wrong, of course. I will just make this some point on the basis of this. Now, look at the result which you have got for the probability of the head. Now that you have done the coin tosses 10 times, the result which you have got is, so half, which is what the value was, plus minus half over root 10. Now compare it with the result which you got for one toss. So if I take one toss and I 10 tosses. So for one toss, this result was 1/2 plus minus half. For 10 tosses, the result turned out to be half plus minus 1 over 2 divided by square root 10. So you can see that your error has reduced on the probability of getting head. Now, if I do the same thing for 100 tosses, what will be the result for the expectation value of this random variable x? How are you going to make it, and tell me what will be the final result? So if I do that 100 tosses, so you do something similar in principle. How the
So
random
using
variable
1/2
right
1/2 plus 1/2 over square root 100.
and that is how much? Basically,
1.
square root of 100 is nothing but 10. Yeah.
5, sir. It comes 5 overall.
Where does some 5? I am sorry, I missed that. Oh, I mean, you are just
Final.
actually multiplying the numbers, yeah?
Yes.
Yeah, but okay, I mean, the point comes here itself if I write it in this manner, that by increasing the number of tosses, and if you are trying to predict the probability of getting head, that probability is getting better in terms of its precision. The value, expectation value is not changing, but the error on it is changing. And that error which is getting more and more precise is exactly what is coming from the central limit theorem. If you remember what the central limit theorem was doing, central limit theorem was saying that the x bar, which is the mean, under the limit n tends to infinity is normally distributed with this mean is same and variance sigma square n when each of the individual reading from which these x bar were let's say distributed, they were each of them were having exi mean mu and variance of xi sigma square. So it is the sigma square term of the x bar which was getting better as you are doing this averaging. And this is precisely the help which is coming from the central limit theorem. That central limit theorem is telling you that when you are averaging over large n, the precision of your number is getting better. Just like what you have seen in the case of if you want to predict the probability of head from one toss, probability of head from 10 tosses, from 100 tosses. So let me just tell you, by the way, if you look at the number which you have seen given me here, which was ex equal to 5 and plus minus square root 5 over 2, that itself is sufficient for me to get all the information, because I can convert it into fractional error and I will see that the fractional error is a small number than as compared to the previous case. In the previous case, fractional error was 100%. In the second case, when n is equal to 10, of course, fractional error is not 100%. Yeah. So what does this mean? This means in a single coin toss, in a single experiment of 10 tosses of a single coin, on an average you will get 5, but there is one sigma standard deviation of root 5 over 2. Root 5 value turns out to be what? 2 point?
Sir, I think sigma is equal to
something.
Say it again. Yes, I think.
I think sir
2.24.
Okay, 2.4. Yeah, somebody else is saying, so let me just hear.
I think sir sigma is equal to whole under root 5 by 2. It comes.
Yes, sir. Yes, it is whole under root.
So this guy, whole under root 5 by 2 is what is coming. So let me just get from everybody. Okay, let me hear from everyone.
Yes, sir.
Is it
Yes, sir.
because n was 10? So either
Yes,
I could have written this as root 10 over 2, or if I just want to take it, it is root 5 over 2. Is it this what you want to say?
yes, sir.
Yeah,
Yes, sir.
absolutely right. Yeah, thank you. So this number, this is going to give you a square root of approximately 1.24, which is still close to 1. So what you are saying, on an average, you will get 5, but there is an error of 5 plus minus approximately 1. Okay, there will be some 1 point something number will come, which is surely better than the one result which you got earlier, that it was 0 plus minus 1. So there the error was 100%. Here, what is the fractional error or the relative error which you are getting? So give me the percentage error.
31%.
So what you must have done is nothing but root 5 over 2 divide by 5, right?
Yes, sir.
Yes, sir.
And this number turns out to be in 200, of course.
31 point something.
31 point? some percent. Okay, let's just put it as 31%. So here it was 100% error on my result, the first toss. Here it is 31% error, which is for n is equal to 10. Can somebody quickly do the same calculations and give me the number for n is equal to 100? So now that you understand it, so for n is equal to 100, expectation value of x is n times p, which is 100 into half, 50, and variance of x, which is np1 minus p, 100 into half, and sigma x will be 10/2, which is 5. Pretty fast. Yeah, I mean, since with 100 it is rather easy to work with, right? So what is the percentage error for 100 tosses?
10%.
So this is rather simple, sigma x over ex, which is 5/50. This is into 100. Okay, just to make complete. So this is 10%. So your error is reducing on what you are now claiming. Earlier you were claiming that the probability I am able to claim with 100% error with one toss, you said that you would be able to claim it better when you go for 10 tosses, and you will be even able to do it better if you go for 100 tosses. Here there is this error of 10% on each. So this is all reflection of the central limit theorem, which says that the averaging improves the precision, and this averaging, as the number goes larger, as n goes larger, this will get reduced to ultimately to the point where your x bar will represent the true mean of the population. So this is what the central limit theorem was, and I wanted to emphasize on it because this error one has to be very clear with. This error is, so we have x bar result plus minus sigma of x bar. This is what we call the error on the mean, and this quantity gets better and better as we are averaging over large n. So questions here with central limit theorem. I did it for the Poisson statistics earlier, which you do it in the class. I mean, this is just, let me just go back and see what we did. So this is what we did for the same thing for our GM counter experiment, that how the error gets better as you are going for large number of averaging. Or now the same thing happens for the coin toss. It's one and the same thing, to be honest. All reflection of the central limit theorem. Questions? Questions on what we have done just now?
No, sir, it's clear.
Okay, good. Thank you. Okay, so this is what I just wanted to finish off before going to the next part of my talk. Okay, my class, which is, I'll have to stop somewhere. Here. Okay, so in today's class in the morning, we tried to do the parameter estimation, and we discussed that statistics, the branch of statistics, which is basically the inferential statistics, which we call up, that's what we discussed. That is that we are able to come up with a method which can help us estimating a population parameter, which is generally unknown, and we try to estimate it from the sample. Now I will start with this next point, and I will of course take it up to the tomorrow's class as well, and I will give you an example also for this. So I will continue to build on this. Decision making. Can we use the inferential statistics to make a decision? Now, as soon as I say this word decision, you will of course ask me, sir, what kind of decision are we talking about? What decision do we want to make? So in order to do that, I have just framed a question. We will read the question, try to understand what is asked in the question, and then I will come up with the topic which I am starting with, which is what we call as the hypothesis testing. So let's just read, and I am reading with you. A company claims to manufacture power banks with mean output of 10 watt. So we have, of course, a regular habit of purchasing power banks, and we are always seeing some companies are saying that they have 18 watts, some others 24 watts, 33 watts, 64 watts. These watts are getting bigger and bigger these days. But okay, they claim that the particular power bank is of this mean output, some wattage. So a company claims to manufacture power banks with mean output of 10 watt. Somehow, okay, this is not very clearly seen here, that the sigma of the mean is given. Somehow it is given, which is 1 watt. That it's saying that we produce power banks with mean output of 10 watt and the standard deviation of 1 watt. Now to check the claim, how to verify that? 20 power banks were randomly selected and found to have a mean output of 9.5 watt. So company claims that we actually have this 10 watt mean output, and 20 power banks were randomly selected. They were tested to have this. Now here the question comes like this. For
Sir, you are not audible.
yeah, my power again, the network connection. Yeah, I could sense it because I was out actually. So anyway, so I'm still reading the question. Yeah. So formulate the hypothesis and check using z-test if mean output is consistent with company's claim at 5% significance level. Now, this is the type of question which we are trying to answer using this hypothesis testing and what we call as the decision making. We are going to take decision. So it is almost as if some inspector is coming to check whether the company claim is correct or not, and that person on the basis of the sample or the sampling will have to make some informed decision whether the company's claim is correct or not. If not, then they will ask company to just change the claim. So this is the decision which somebody will have to make. And that is how actually the decisions are made. It is not done by testing everything what is done, because that's what company is doing and you never know what the company is actually doing. But randomly selecting certain samples, and you would be able to make some decisions on the basis of that. So this is the type of question. But if you look at this, the dissection of it is this, which is what I am going to do soon. First, the claim is about the mean output. So it is about some average quantity, which here is some mean. The claim could be about the standard deviation. The claim could be about anything else also, depending on the parameter. Here it is about the mean output. And mean output of what? That all of what they are making. So that is, the claim is about the mean output of the population. That we are saying that all what we are making, that will have the mean output of 10 watt or the average output of 10 watt. The claim is about this population parameter, which here is mean. Okay. To check the claim, 20 power banks were randomly selected. So what we are doing here is sampling. Right. So 20 power banks were randomly selected and they were found to have the mean output of 9.5 watt. So you actually did the measurements on these 20 power banks and you find that it is having 9.5 watt. And we have to now check whether what the company is saying or the company is claiming, if this 9.5 watt is consistent with that. So somehow there is this mean parameter of the population, and we are going to take this sampling, and from this we are trying to say something about the claim. Then I am using the word at certain significant level. This means that I cannot completely refute or accept the claim, but that claim or whatever we are going to do, this will be done at some significance level. So this is something which we are going to soon see what it will mean. And the test statistic is actually here told to us that we are going to do z-test. It just means normally distributed test. I will discuss that portion also. But I wanted to highlight the kind of question we are trying to attempt, that what is about the decision making we are going to discuss. We are going to discuss the decision making on some population parameter, which is mean, on the basis of the sample average or sample mean taken, and then we will compare certain things using the statistics, decide whether it is. So first, I would let you ask questions on this question itself so that I can just think about what are the things which come to your mind. We are going to dissect, of course, I mean, just like the way I said. So decision making or called hypothesis testing. So what is it about? It is about the hypothesis about a population parameter we are going to consider only this in our class. We are not going to go beyond the mean because of the limited time. But as you can think of, decision making can be done for any parameter. And one has to think about it on that particular aspect. But we are going to restrict in our class just the hypothesis regarding a mean, as given in the question, mean output of the power bank, for example. So we construct what we call as, this is the first step, we construct what we call as the null hypothesis, which is represented by something called H0. And we say null hypothesis that whatever the company claim is, so in our question it is 10 watt. So null hypothesis is that the company, whatever company claims is. And then there has to be an alternate hypothesis, which we call generally as H1 and HA, and that is whatever the company is saying is not correct. So ultimately our job is to either accept the null hypothesis or reject the null hypothesis. Or in other words, accept the null hypothesis or accept the alternate hypothesis. Here the alternate hypothesis is, okay, whatever the claim was, that's wrong. Now in order to do that, of course, we need our statistics. We need some evidence, you can say. Yeah. And that evidence is coming from our sample. And what is the sample? Sample average is something which we are going to use, which we call as X bar. Now, from the laws of probability and statistics, what do you know about the sample averaging? This is the question which I am posing to you guys. What do you already know about this X bar? Do you know anything about this X bar? If you take a sample from a population, do we know something about it?
So it's given 9.5 watt.
Yeah, the value is given, sure. But even if I do not give you the value, do you have some idea how this sample average is generally distributed?
So it's random.
It's random, sure. But for large sample, I did say something. This is the average. It is
So
It's normally distributed.
It is normally distributed. So one thing is that X bar under large N, and I will also add known sigma of the population parameter. Under this, it is going to be normally distributed. Normally distributed about some mean. What mean? What mean? Normally distributed about what? Because normal distribution has to have some mean and some standard deviation. What is the mean about which it is distributed? About what? याद करो भाई, सेंट्रल लिमिट थ्योरम क्या था? X bar normally distributed about which mean?
Mu.
Yeah, population mean, right? And what is the standard deviation or variance?
Sigma by
ये तो
n.
आपको, right, sigma square over n, भाई ये तो याद रखना पड़ेगा. Standard deviation sigma over root n, you cannot forget it. So why we are using a particular statistic x bar? Because we know from the central limit theorem that x bar is distributed normally about the mean, population mean, and having the variance sigma n. So what do? What we do is that we divide this whole plot something like this. And you will say, sir, how this point? I will just come to that. And what we say that if the x bar value, whatever value we have got, 9.5 watt, if it falls within this region, then I will accept the claim. That means I will accept my hypothesis, null hypothesis. However, if the x bar value lies in this small region outside, then I will say that I will reject the null hypothesis. So what is expected for any sample mean? That sample mean is going to be distributed normally around the population mean, and hence the sample mean will be able to give us some idea whether this original hypothesis, that mean mu is equal to 10 watt, which was the null hypothesis, whether that is right or not. So this is what we are going to do in the decision making, that we somehow construct this region within this, and then we say if our x bar, what we have measured, falls within this big area, then we will accept the hypothesis. That means that there is more probability that x bar has come from this particular population mean. But if it falls under something else, I mean this small region on the two sides, then we will not accept the hypothesis. So this is what the evidence-based hypothesis testing or informed decision making is. So somehow we know, we know that x bar is going to be normally distributed and we are going to take advantage of it. So this is the whole idea. And now, how am I going to choose these two portions? This is the portion which is basically coming. If you remember in the question that there was something which was given as level of significance. So the idea of these guys, where am I going to put this? This is done on the basis of the question's level of significance. That at what significant level you want your claim to be correct. So let's just try to understand this portion. But please go, let's just read the question again. If the, what was the question towards the end? If mean output is consistent with company's claim at 5% significance level. So I am interested somehow that these be placed, these 2 points be placed at the 5% significance level. And that's what I'm going to, of course, discuss next. However, the overall understanding is just coming from our central limit theorem. that X bar has to be normally distributed about the population parameter. So I can make some informed decision from this X bar. Fine. So now let's just try to understand this level of significance. What is meant by the level of significance? Probability. So I am going to write down from this. Let me just choose this point which I am using this arrow. So mu minus, I am giving some interesting name, Z alpha over 2, interesting name, times sigma over root n. And I am here giving mu plus Z alpha by 2 sigma over root n. And I am just going to now make some interesting things. So this point, what is this point? I am calling this point interesting, this Z alpha by 2. And you will ask me why this interesting now. So tell me something. This probability, the probability that what my undo, my eraser, this kind. The probability that mu lies between mu minus sigma and mu plus sigma. What is this probability? Do you remember?
0.68.
Yeah. First, a simple question. Yeah, 0.68 I am just going to write down. Is this the second one is correct or the first one is correct, by the way? That is the first question. And what does this mean? I should just write this. Yeah, okay. First one is correct or the second one is correct? Which one of the two? One is correct, one is wrong, of course.
Sir, second one is correct.
Second one is correct, sir.
Okay. So can you remind me how X bar is distributed? Normally with mean mu and variance sigma square over n. How individual X is distributed? Mean with this. I am going to make this X bar. I am writing explicitly X bar. Yeah, I'm not writing any individual reading. I'm trying to talk about the average of some. So which one should be correct?
Upper one.
See, so one thing you have to keep on thinking about, because my central limit theorem is very important. Whenever I am talking about the sample average, the standard deviation for the sample average is sigma over root n. So if you put n is equal to 1, then that is exactly what is there for a single sample. Yeah. If of course I am going to make the average, then I am going to put this sigma over root n. So please remember that the second one is not correct as long as you are writing X bar. And we are talking about our X bar. Okay, this is 0.68. What is the probability? This. So twice of that. Mu minus 2 sigma to mu plus 2 sigma of that.
Sir, 0.95.
0.95. What does this mean, by the way, this 0.95? What does this mean? What does this mean? So in the curve, if I am going to draw, what does 0.95 mean?
95% area is covered.
So 95% area is covered. Right? probability that this X bar comes from the mean, which is a population mean, minus twice of the standard deviation or plus twice of standard deviation, that probability is 0.95, and there is only 0.05%, not percent, 0.05 probability that it is lying outside it. This is precisely what we are going to take help with. So what we are writing is this: probability mu minus, now Z alpha sigma over root n. This is about the level of significance what we are going to talk about. Mu plus Z alpha sigma over root n, and I am using even the word root 2. This is equal to, I am defining it as 1 minus alpha, where this alpha is level of significance. Okay, what does that mean? That means probability that X bar is greater than equal to mu minus Z alpha over 2 sigma over root n. So this, or what will be this?
Alpha.
This is equal to alpha, and this means that the probability that this X bar, which is less than equal to this, or X bar greater than equal to the right hand side, that value is what is defining my level of significance. And I will tell you why this symbol is looking so cumbersome right now, because generally we talk about the standard normal distribution, right? And if you talk about the standard normal distribution, how do we create that standard normal variate? Z, if I want to create it from X bar, what is standard normal variate? Normal distribution with mean 0 and
Okay.
standard deviation of variance 1. So if I want to build this for X bar, which we built for our central limit theorem, what will be this? X bar?
Minus mu divided by sigma.
No, minus mu divided by, again go back and you will look into the central limit theorem. It is whatever the standard deviation we had for this X bar, and this is sigma over root n. So if you want to write down the same formula, let's just write down whatever you have written, this formula. If I want to write down the same formula for X bar minus mu divided by sigma root n, so can you help me writing it down? Please try to do it on the piece of paper. I want to write down the same formula, but for this probability less than equal to X bar minus mu over sigma over root n. What is this? So just subtract minus mu on all the three inequalities and divide by sigma over root n.
Minus Z alpha over 2 to alpha over 2.
So here it will be minus Z alpha over 2, and here it is
Z alpha by 2.
right, which is equal to 1 minus alpha, right? So which is same as writing set, which is what you have constructed. So this, of course, I can also write down like a simple one. And I can also write then mod Z. What about this greater than Z alpha by 2? This should be
Alpha.
Right. So please see that if I convert my x bar into this z variable, which is nothing but the standard normal variate, then in that case that z will be distributed about this 0 with minus z alpha over 2 and plus z alpha over 2. So alpha, what is defined as the level of significance. Now in the question which is given to us, we have to test our problem. So let's just see at 5% significance level. What does that mean? It means that we are going to use alpha value to be 0.05, and that means that we will figure out the value of z alpha by 2 and z alpha by 2 on both the sides, such that the total area under the curve of the two sides will curve out to be alpha. So we will place our z alpha by 2 in the manner such that the area under the curve, which is on the left hand side and the right hand side, that turns out to be 0.05 or 0.025. So this is what we try to build by saying that we are going to test our problem at some significance level. So all we want to say that the probability that our x bar comes out from the mu, from the normal population, that x bar resembles the population mean at 95% level of acceptance and 5% level of rejection. So my x bar, if my x bar will fall anywhere between this 95%, I will accept and I will reject if this guy falls in any of the region. So this is what I meant to say when I said, so undo and previous. If you look at this page, look at the plot. When I write the accept x naught and I wrote my mu minus z alpha by 2 sigma over root n and mu plus z alpha by 2 sigma over root n, then what was this z alpha by 2? This z alpha by 2 corresponds to the placement of the critical points such that if the x bar lies in the critical region or outside this portion, then we are going to reject the claim. If it lies between it, then we are going to say that we are going to accept the claim. So if we are saying that we are going to do it at 95% level of significance, then we are going to place it somewhere. If we are saying that, okay, we want to do it at 90% level of significance or 68% level of significance, all we'll have to think about where are we going to do this z alpha by 2. This is something which has to be decided before you are going to actually do the sampling. In principle, you should do that before doing it. So at this point of time, I have just told you that there exist three aspects of the three steps of the hypothesis testing. We are going to make a hypothesis about a population parameter mean, which is our null hypothesis. We call the null hypothesis as whatever is claimed, and the alternate hypothesis is that the claim is not correct. We then use our statistics knowledge and we say that the sample average will be such that it will be distributed normally about the population mean, and hence if the x bar lies anywhere far off regions, then then what was the claim of the company? That's not correct, and we are going to reject the claim. We are not going to accept the null hypothesis. But in case if it falls in any of the region in between, then we will say that it will fall, that is the null hypothesis will be accepted. So I will build on this problem tomorrow. Of course, I will continue to build on this problem tomorrow. We will solve this problem and see what we are going to do. But regarding the three things which we have done, please feel free to ask questions. Particularly the level of significance is what makes something interesting. Anybody? So no questions. That means that you are still going to understand this concept once I am going to solve this problem. The whole of the gist of solving the problem lies in one single point. Somehow we know that X bar, which is the sample mean, that according to CLT is distributed normally with mean population around the population parameter and the width, which is sigma over root n. This is something which we know, and hence we are going to utilize that. Okay, so tomorrow when we will be solving this problem, after I guess maybe after that you will have questions and we will do that. Fine. Okay, guys. So for the time being, I will stop here.
Okay, sir.
Thank you, guys.